Okay, we're back with chapter 9, and this time we are looking at an AC circuit and our lab 9. And for lab 9, we're looking at an AC circuit, and we're going to set our frequency at 300 hertz, 500 hertz, 1 kilohertz. We're going to go up to, I think it says to 4 or 5 kilohertz, but we're going to go through a number of different settings for kilohertz. What you're going to see is you have your input waveform, and then you have an output waveform that starts to shift, and it goes down. So it's going to shift. So if you have a value, like this would be your 0 starting point, and this would be 90 degrees, your output waveform is going to shift, and it's going to have its peak someplace over in here. So what we want to do is we want to measure that shift, and it would be from here to here is 90 degrees, and if our peak hits right about in here someplace, it's that percentage of 90 degrees. So we're going to say if this is 90 degrees, if the peak hits someplace in here, this would be maybe 30, this would be maybe 60, and that would be 90. So we're going to have to guess approximately where that peak is, but we're going to look at it and we're going to say what percentage of 90 degrees it is. So that's where we're going to be with this lab. So let's go over and let's look at this. Let's look at it now, and let's get an idea of what we got here. So hang on just a second, we'll get set up. We'll be looking at it in a second. Okay. Okay, we're getting our lab book here and on the other page. Alright, so this time we're looking at a waveform of an input, and this is our input waveform right here. It's a sine wave, and I can change the frequency of the sine wave, and right now it's at 100 hertz. So you can see that the input waveform, it says set the input waveform at 10 volts peak to peak. So we have 2 volts per division. Here's our 0 point. It's almost up to 5 divisions, so that's 10 volts peak to peak. So we've got our input set at 10 volts peak to peak, and we can measure the amplitude peak to peak of our output. Here is our physical inductor. Here it is. And here is our input signal, and that is the signal in the yellow. The yellow is the input signal, and the green is our output signal. That's from the second channel, and that's the signal that's coming in as our output, or the value across the 10K. So basically in this situation we're looking at voltage across the 10K, and we're asking what is it going to be doing as we go up in frequency. So it says start at 500 hertz. I wanted to show it to you at 300 hertz because at 300 hertz you don't have much of a phase shift. Here's your initial value, and here's your phase shift over, and it's from this point to this point is 90 degrees. So with 300 hertz we're maybe 10 or 20 degrees off, but not very much. But now I'm going to go to 500 hertz, and I want you to watch the change. Okay, we're going to go over here and we're going to measure it. See the jump between 300 and 500 hertz, where it was the peak of the output here is very close to the cutoff. So here's our 0, and here is 90 degrees. So from here to here is 90 degrees, and we're almost to 90 degrees. We're maybe 80 or 70 degrees out of phase. So our phase angle changed dramatically when we went from 300 to 500, and also our amplitude went down a little bit. It's now about here's 0 to 10, and we're a little over, maybe about 3, from about 1.2 down to about 1.5 up. So that's about 2.7 or about 3 volts amplitude. So that's our peak to peak of our output is about 3 volts. So input is about 10, output is about 3. So let's go now to 1K, 1000 hertz, and watch the change again. So this is going to be at the I just got 100 hertz, so that's, I went backwards. 1,000, Ted. Okay, so 1,000 hertz. Now watch the change. See, the peak of the output is almost at where it cuts through the zero. So here's our 0 point, and here's at 90 degrees, and our peak is almost to 90 degrees, so we get closer and closer to 90 degrees. And also our amplitude has gone way down. It was at about 3, now it's definitely less than 2, and it's about 1.5. So at 1 kilohertz, our amplitude is about 1.5, and our phase angle is 80 or so, 80 degrees. So let's go now. It says at so it says repeat this at 1 kilohertz, 3 kilohertz, and 5 kilohertz. So 1 kilohertz, we're almost there at 3,000 hertz. Excuse me, 3,000 Ted. See how much the output has gone down, and we have to adjust our input a little bit because we have to adjust it down a little bit. Okay, it's adjusted down a little bit, but see, our output is almost well, it's just almost at 90 degrees. So there's our output at 1,000 hertz. Okay. So we're basically at our very low. We're almost at 90 degrees. So the peak of the output is almost where it cuts over on the x-axis for the input voltage. Okay, so let's go to 3,000 hertz. So I'm going to go 3. I'm just going to hit the kilohertz on this one. Okay, and for this one we are at the 90 degrees. We're basically at 90 degrees. And we've almost lost all of our amplitude, so it's almost to nothing, our amplitude, or output amplitude is. And again, at 5 kilohertz, excuse me, even less. We're even less on our output. So you can barely see an output at 5 kilohertz. So it also says connect the. Also, let's go to point. So this is part 5 where it says connected to B and all that sort of thing. Now it says reverse the polarity of the source such that the ground position is at point A. I'm not going to do that. It's not necessary. That basically it shows the same answers as we would have with above. So we're not going to find anything new. So you can skip 6 and 7 and just do 1 through 9 except for 6 and 7. So that gives you an idea about the this AC waveform. It shifts, and as you get higher in frequency, you get more resistance from the inductor, and the amplitude of the output goes significantly down. So this is a shift and amplitude killer for an output signal, as opposed to just a high. The DC was a rise and a tau and that type of thing. Now we're away from that, and these are questions that we're going to be talking about in chapter 8 and 9. So take care and have a good day. Hello, we're doing lab 10, and we're looking at the various components in this lab, and this is a DC charging lab with a capacitor and a resistor. So the resistor that we have is a 470 ohm resistor, and the capacitor is a 10 microfarad capacitor, 10 times 10 to the minus 6th. So those are the two values that we have. We measured the resistor, and it was 467 ohms instead of 470. And we measured the capacitor, and it's an electrolytic capacitor, but we measured it at 9.09 microfarads. 9.09 times 10 to the minus 6th. And here we have a 10 volt signal over here on this wave generator, and it is set up right now at 10 hertz. So every tenth of a second it's switching on or switching off. So we have the scale here is 10 milliseconds per division. So it would be 10 milliseconds from here to here, 10 from here to here, here to here, here to here. So it goes in 50 milliseconds it turns on, and 50 milliseconds it turns back off. So now you can see the RC time constant. The RC time constant starts here, and it comes up, and right about here is about the point that we want to look at, and this would be about 60% right in here, and that would be if this is 10, this would be about 3 or 4, maybe 3 milliseconds. So basically, our time constant is tau, or RC, is roughly 3 milliseconds. And if we multiplied our numbers out, we have 10 times 10 to the minus 6 times 470, and roughly that's 4.7, or a little bit longer than that, but it's in the range, so we're close. This is we could lie and say it's 4.7. We could say it's whatever you want, but it's in that range. So this would be somewhere right about in here is a 63%, and that comes down here, and we go over here, and we could say it's 4, we could say it's 5, we could say it's 4.7. It's in that range. So that is our circuit, and that's our output, and you can write up your description based on those variables. Thank you. Have a good day. Good morning. We're working with a diode in this lab, and it's a 1N4007 diode, and it's right here in the circuit. We've already put it in the circuit, and you see the little stripe on it, and that's the downstream side, or that's the forward direction. So our current positive flow is from around through the resistor and then back to 0. So we have our power supply over here set up at 0 volts, and we are reading over here with the voltmeter, and we're basically going to be taking readings of volts and then current based on different settings of the power supply and the power. So we're going to put some jumpers in to make it a little easier to get these readings. So I'm going to put a jumper at each of these 3 points so that we're not when we do these readings, the voltage readings, we're not touching the actual devices. We're just touching these sensor these extra points. So we're going to try to set this up so that it's a little easier to be able to do this reading. So this would be the readings across the diode, the voltage across the diode, and this would be the voltage across the resistor. So we're going to start. I'm going to go in 0.1 increments from 0 up to 1, and then 2, 3, 4, 5, 6, 7, 8, 9, and 10 volts. I'm going to read the voltage across the diode and then across the resistor at each of these points. So we're going to do that, and I'm going to leave the one lead on the middle, and I'm just going to touch the other side. So this reading, well, the reading across the resistor will be a negative, but just ignore the negative, and we're gonna just touch the one and then touch the other. So we're going to do this as easily as possible, but yet at each station you're gonna be told 0.1, 0.2, 0.3, and then the voltage across the diode and the voltage across the resistor. So here we go. We're at 0 volts on the A scale. We're going to measure the voltage now across the diode, and it's a little negative, but there it is at 0. Voltage across the resistor. Okay, now we're going to go back and we're going to go to 0.1 enter for this voltage. Voltage across the diode. Voltage across the resistor. Ignore the minus sign if there is one. Okay, now 0.2. Voltage across the diode. Voltage across the resistor. Ignore the minus sign. 0.3. Voltage across the diode. Voltage across the resistor. Again, ignore the minus sign. 0.4. We just have to remember to hit equals or enter. 0.4, there's the voltage across the diode. Voltage across the resistor. Ignore the minus sign. 0.5. Enter. Diode. Resistor. 0.6. Diode. resistor. 0.7 diode, resistor. If you didn't get the diode one, this is a diode one at 0.7 again. Diode, resistor. 0.8 diode, resistor. 0.9 diode, resistor. It's in this area that the change is starting to occur, that you're going to see it going from a low resistance to high, from low current to high current, and it takes off and it goes to low resistance. So this is in this range, right in there. You'll see it if you graph it. You'll see it. Okay, now we're going to go in 1 volt increments. So we're going to go to 1.0, 1.01, enter. 1 volt. Voltage across the diode. Voltage across the resistor. Again, ignore the minus sign. 2, enter. Diode, resistor. 3, enter. Diode, resistor. Ignore the minus sign. 4, enter. Diode, resistor. 5, diode, resistor. 6, diode, resistor. 7, diode, resistor. 8, diode, resistor. 9, diode, resistor. 10, diode, resistor. So we could go back and measure current, but we realize that we've got a 1K resistor here. If you measure the voltage across it, you're going to get the current in milliamps. So all you have to do is take, it's a very accurate 1K resistor, so all you have to do is take the voltage across the resistor, divide by 1,000, and your answer is in milliamps. We could prove that by just breaking this circuit apart, but we don't have to. We know that the voltage across the resistor is V equals IR, so I is V over R, and we can get our I that way. So you basically have now all that you need for the answers for the voltage and the voltage across the diode, voltage across the resistor, and the current through the circuit in the forward direction. Now it says connect it backwards and go in 1 volt increments and do it again. So basically we're going to turn this guy, we're going to go to 0 volts, and we're going to turn this guy around so he is the other way. Once we do that, we're going to find it's very different results, because he's now just a blocking diode. He's basically just going to block current. So we're going to put him in the other way around, put him in with the other side, and we're going to measure the voltage, and we're going to measure across the diode and across the 1K resistor, which gives us the current. Okay, so basically we're going to go through, this time all we have to do is go in 1 volt increments. We do not have to go in the 0.1, 0.2, 0.3, 0.4, 0.5. because we're going to see that it's going to be pretty similar the whole way through. So again, we're going to hook up the black to the middle, and we're going to basically just go between the two with the red, but again, ignore the minus sign. So we're now at 0 volts. We're at 0 volts, and we're going to measure the diode here and the resistor here. Okay, we're going to go to 1 volt, 1, enter. So this would be for the part where the diode is reversed. Okay, and that is across the diode, this is across the resistor. Go to 2, the diode and the resistor. Go to 3, diode, resistor. Go to 4, diode, resistor. 5, diode, resistor. 6, diode, resistor. I should go back. I didn't hit enter, so this is 6 again. 6, enter. Diode. Diode at 6. Resistor. 7. Diode. Resistor. You see there's no current. It's blocking. 8. Well, the voltage goes across the device. That's not... Okay, this is 8. 7.99 across the diode. And no voltage across the resistor. There's no current. That's 8, 9. Oops, I should have hit down here. 9. 9 volts. That was the diode. This is the resistor. 10. Diode. Resistor. There's no current. So now you're being asked to graph the voltage across the diode, the voltage across the resistor, and then the current for each of these. Follow your directions, but you now have all the information you need to finish this lab, and look and see if basically is this a linear or a nonlinear device, and it's very nonlinear. Okay, take care and have a good day. Hello, we're working on exercise number 12, the NPN transistor, and I'm going to show you a small transistor here. Right here it is, and you can see the 3 leads. There's 3 of them, and they come out the bottom. And if you look at it with the flat side to the right from the top, the first one is the emitter, the second one is the base, and the third one is the collector. So it's EBC, emitter, base, collector. And I've already hooked this circuit up. This is a 2N 2222 NPN transistor, and it's located right here in this circuit. You can see it. It's already set up. It's right there. And I've got a 2.2K resistor from my 12 volts to the base. Excuse me, from the 12 volts to the emitter. I've got the base connected directly to the frequency generator over here. So this is coming directly out, and it is set at 5 volts, but it doesn't really produce 5 volts. It's at 1 kilohertz, and it's producing, we're going to look over here at the scope in a minute, it's producing about 2 volts of voltage. But I want you to notice what's happening, because the emitter coming off of here comes over to the green in the output, and this is the first time you've probably seen this, where we're actually amplifying a circuit. Now this is acting as a switch. So this one is turning off and this one is turning on. This is my input. It's between 0 and 5 volts, and it's about, this is 2 volts per division, so we're a little less than 2 volts input. So that's our coming in from our signal generator, and this is going out from our output. So we're actually producing a signal that comes out at, when this one turns off, this one turns on, so it's 180 degrees out of phase. So this one's out of phase with this one, off, and this one turns on. But look at the voltage. This one is 2 volts, and this one is 5 volts per division, and it goes a little over 2 divisions, so it's about 12 volts. So that's pretty well matches our 12 volt supply, which is set up over here as 12 volts. So basically what we've done is we've amplified a signal and we've switched it. 2 volts on, or 2 volts off, 12 volts on. 2 volts on, 12 volts off. So we've actually created a switching circuit. This is a transistor being used as a switch. You can see it. It's actually switching the exact circuit. And this is at 1 kilohertz, and we could try it at various frequencies and it would work much higher frequencies, but at least you get to see it at 1 frequency here, but it will work across the band of a number of frequencies. But this is using a transistor as a switch. Take care.